All right, good morning, everybody. Um, so today I couldn't be in class, so I decided to screen capture this. And Miss Tina is going to be in class today to go over this with you. So at any point, if something isn't clear, please feel free to raise your hand, and she can stop the video and go to the board and give a better explanation than maybe I could through the PowerPoint. So today we'll cover the remaining information for Chapter 17 that I will hold you responsible for prior to the exam. And Friday, if I remember the schedule correctly, we will have a review for the exam. So everything that is covered today in lecture will be fair game on the next exam. So we will have a demonstration on Friday in addition to having the review session. So today we're going to continue to talk about amides. We'll talk a little bit about acyl substitutions. I'll talk a little bit about that in terms of biology, and then we'll talk about some other things that might be of interest to many of you. So we all know that amides are carboxylic acid derivatives, and it turns out that amides can actually be hydrolyzed to carboxylic acids and free amines, either under acidic or basic conditions. Now, this is not a easy reaction to do because we know that the amide bond is actually quite strong. This is the bond that is used in proteins and peptides, but nonetheless, these can be hydrolyzed to carboxylic acids and amines. Under acidic conditions, of course, you're going to get the free carboxylic acid and the protonated amine as a result of the leaving group here. But under basic conditions, you're going to end up getting a carboxylate and the free base of the amine. So let's look at some examples here. Here we can take this primary amide, we can hydrolyze it, get ammonium and acetic acid. This is under, of course, acidic conditions. Now, practically, this has to be done by taking the amide, placing it in water with some concentrated acid, and typically boiling this over a period of time for this to actually occur efficiently. Same thing for basic conditions. Typically, you have to boil this to get this to occur. And of course, here we would get the benzoate and the free base amine, the methylamine. The mechanism is pretty straightforward. The hydroxide under basic hydrolysis will attack the carbon of the carbonyl, break the weak pi bond. You end up with a tetrahedral intermediate. The intermediate then collapses and you lose amide, not amide, but amide, NH2 minus, which is a strong base, by the way, and will quickly deprotonate the resulting carboxylic acid to give ammonia and the carboxylate anion. Now, all of these reactions are reversible, and except for the last step, because of course this is a gas. It turns out that the equilibrium actually does not lie to the right in these because amide is a very, very strong base. So if you look up the pKa of the base, it's somewhere in the 30s. If you look up the pKa of hydroxide, it's somewhere around 16, right? So we have a weak base providing us with a strong base, and that is not a favorable reaction. So the equilibrium does not lie this way. What drives the equilibrium is the fact that this last step is not reversible, and so that's what drives the reaction in this direction. But nonetheless, this is considered a very slow reaction, actually. Other amides that are important for us are the beta-lactams. So we talked about lactams last time. This is actually penicillin. So you can see that it actually has two amides. So this is we'll call the regular amide. So it's not part of a cyclic structure. And here, of course, is the beta-lactam. This amide is actually quite reactive, more reactive towards nucleophiles than a typical amide. And so can anybody tell us why this particular amide is so reactive? Okay, so that's right. So it's because of ring strain. So this is a very strained system. It's a four-membered ring, and this bond is actually easier to break than, for example, this bond. And so it's this bond of penicillin that is actually responsible for the antibiotic properties of penicillin. In fact, this has to be present for these antibiotics to work, and this is called the pharmacophore. So it's what is pharmacologically necessary for penicillin to function. The way that this works is in bacterial cell walls. You actually have these individual polymer chains, and you have this protein, or this enzyme called transpeptidase, which actually links a primary amine with a carboxylic acid to make an amide, and it cross-links the cell wall, making it very, very rigid. But what penicillin does is it actually interferes at this step with the transpeptidase step, and it keeps transpeptidase from doing its chemistry. And if a bacteria has, of course, a weak cell wall, it is then very susceptible to being destroyed or killed by the immune system. And so that's how penicillin works. It works by weakening the cell wall of a bacteria. So here we have the enzyme transpeptidase, and so there's a free amine that's responsible for the catalytic activity of transpeptidase, and it will actually react with the lactam of penicillin, goes through this type of chemistry, and now we no longer have that free amine that can do the catalytic chemistry of transpeptidase. And so penicillin's job is to actually go in and irreversibly inhibit the transpeptidase enzyme. So you all need to know this table. I would commit this to memory. So this is what we can do with the various acid derivatives. So for example, if you look at here on the top, we have acid chlorides, acid anhydrides, carboxylic acids, esters, and amides. And over here we have the same thing, right? And so if you see a check, actually a reaction will occur, and if you see an X, no reaction occurs. And these are, of course, where it's the same. So ester and ester, there's not going to be a reaction. So here this tells us that we can take an acid chloride and we can convert it into an anhydride, a carboxylic acid, an ester, and an amide. So what would we need to convert an acid chloride into an anhydride? We would need a carboxylate. What would we need to convert an acid chloride into a carboxylic acid? We would need water. And so you need to go through this. You need to know that you can't convert an ester into an acid chloride. I would spend some time actually memorizing this table. It will definitely help you on the next exam. Some of these functional groups that we've been talking about, the carboxylic acid derivatives, are actually quite useful in making natural and synthetic fibers. So for example, if you look at wool and silk actually is a polyamide. It is a protein. And cotton and linen, fibers like wool and silk, we get these, of course, from things like hair from animals, and they're actually very good materials. They're actually quite tough. Silk and wool are actually quite useful. Cotton and linen, we derive those from carbohydrates, and so those are quite different. So we get that from cotton, obviously, but which is not a carboxylic acid derivative. These, however, that you see here are actually quite useful, and we can even make synthetic versions of those. So for example, this is known as nylon 6,6. Nylon, as you know, is a very tough material that's used to make rope and other plastic materials. It's used a lot on ships, for example, so a lot of nylon ropes are used in places that it might come into contact with water because the amide bonds are so hard to hydrolyze that they're actually quite stable. They hold up quite well. Nylon is actually quite easy to make. This used to be something that we used to do as a demonstration. Haven't done it in a few years. So you take a diacid chloride and you take a diamine and you simply mix it together and it makes a nylon rope. And the cool thing about this is you can mix these things together very carefully and you get a layer. And where these two layers meet, so where the amine and the acid chloride meet, you actually get a thin film of the polymer, the nylon polymer. And you can take something like a knitting needle or a piece of wire with a hook bent into it, and you can reach down in there and you can pull the fiber out of the beaker and actually make a nylon fiber. And we used to do this when I was in high school. We did this as part of our competition to see who could make the longest fiber without breaking it. And you can actually make these things quite long. So we had people that were making these that were 10 feet long, 20 feet long, very easily by this simple technique of making nylon. Dacron, is a useful polymer. So polyethylene terephthalate is its actual name. This is made from, this is a polyester, and it's made from alcohols and carboxylic acids. Very useful in making things like Coke bottles. Mylar balloons, things like that are very useful, commercially useful, and made very easily from this. This is made by a simple Fischer esterification, just like the Fischer esterification you all did in lab, except instead of using benzoic acid, they use terephthalic acid, which actually has these two acid functional groups, and then ethylene glycol. Again, a very cheap, readily available alcohol. This, of course, is useful as antifreeze. So you mix these two things together and you add a little sulfuric acid catalyst, and you can make polyethylene terephthalate through a Fischer esterification process. And so this reaction works very, very well. You can make the plastic sheets, and then you can convert them into very useful things like Coke bottles, etc. This molecule is lycra, also known as spandex. So spandex isn't as popular today as it used to be, thank goodness. But you can see in the functional groups, you have very similar things to what we've been talking about, carboxylic acid derivatives. And so spandex actually has two regions. It has a rigid region, or rigid segment as they call it here, that kind of holds its shape, and then they have a flexible portion. And so this allows it to remember that it has a particular shape, but allows it to stretch, which is what spandex does. And so it's a very strong polymer. It's very useful. It has more uses than people understand. And at one time it was very popular for exercise clothing. People, for whatever reason, enjoyed wearing spandex because it gave them additional support while they were exercising. So let's talk about some biological acylation reactions. So I told you yesterday, or Monday I should say, that biology does a lot of acyl transfer reactions or acylations for a variety of reasons, signaling and other things, making molecules of importance. But we can't really deal with acid chlorides in biology. It's just not compatible. And so if you look at this molecule, what you'll see here is this is called acetyl-CoA, or acetyl coenzyme A. And this is a pretty complicated little molecule, but the organic part that's really relevant here is just a simple acetyl group, or an acyl group with just a methyl group. And really this whole part here makes what's known as a thioester, which is very reactive. Kind of like an acid chloride, but not as reactive as an acid chloride. And so if you look at this, this is really nothing more than a leaving group. This is a huge leaving group, but it's biologically relevant because we have the biologically compatible molecule here that your body can handle, and you don't have to worry about the toxicity of things that might occur with things that are stronger, like anhydrides or acid chlorides. So again, the thioester, the sulfur part is a pretty good leaving group. And so acetyl-CoA will react with a variety of nucleophiles to acetylate or acylate those particular nucleophiles. So for example, acetylcholine is a neurotransmitter. But you know what? You really don't want acetylcholine to build up in large concentrations in the human brain. It will cause you to basically, kind of go crazy if you had large excesses of this concentration of this neurotransmitter in your tissue. And so the human body makes this as needed. And so it's actually a reaction between an alcohol of choline and the acetyl group of acetyl-CoA. And so we can actually make this in the lab. If we took acetyl chloride, which is just an acid chloride, plus this alcohol, it would make acetyl-CoA, or excuse me, acetylcholine. However, biologically, we use acetyl-CoA and choline. This is going to function as our leaving group, and we're going to make this neurotransmitter as needed to do this kind of stuff. This is also useful for acylating and making esters of cholesterol. So cholesterol actually gets packaged in LDL and HDL particles, so low-density lipoprotein or bad cholesterol, HDL, high-density lipoprotein, which is good cholesterol. And the way that the human system makes this is by taking cholesterol, which has this secondary alcohol, and there's an enzyme that reacts this with acetyl-CoA and actually makes this ester. So again, the CoA part is just a very convenient leaving group in biology. And so you can acetylate or acylate these cholesterol molecules, make these cholesterol esters, which then get packaged in these low density and high density lipoproteins, and then they get transported in blood. And these are considered the bad cholesterol, the LDLs, because they're not very tightly packed and they tend to fall apart and deposit cholesterol, which is nothing more really than just a bunch of fat, on our arterial walls and cause these plaques that lead to heart attack and other cardiovascular problems. So we've already talked a little bit about nitriles, so I'm not going to spend a whole lot of time on this. You all can go through this on your own. These are some biologically relevant nitriles. You can do some Googling on it if you're more interested in those. We talked the other day about being able to make nitriles from SN2 reactions pretty easily. So nothing new there. And we talked a little bit about, the other day that nitriles can be hydrolyzed into carboxylic acids under either acid or base conditions. And I told you that this works really well on paper, but this is actually fairly difficult to do in practice. Requires substantial boiling in water and doing some other things that just don't make this particularly practical, although on paper it works just fine. And here's why. The mechanism, if you look at the mechanism, of course, here's the hydrolysis of a nitrile using hydroxide. Hydroxide, which of course has a pK of around 16, has to attack, break the weak pi bond. You end up, again, generating a stronger base than you start with, so the equilibrium is not particularly favorable. So this is kind of the slow step. The nitrogen anion then gets protonated. You make what's called imidic acid and hydroxide. The hydroxide then deprotonates. This then goes through this intermediate, which is in resonance with this resonance structure. This, of course, is not particularly favorable. It gets protonated. You end up with an amide, and then the amide undergoes hydrolysis to the carboxylic acid. So there's a lot of steps here in this particular reaction. And it's just not favorable on a pKa basis that this should occur readily. It does occur, but again, I've tried this reaction numerous times throughout my career, and in each case it didn't work very well at all. It did work, but it was not something that you wanted to build your synthesis on. I'm going to skip this. We've already talked about this in previous chapters. We've talked about this before. So the fact that we can convert nitriles into ketones by reaction with Grignard's or lithium reagents, we've already talked about that in the previous chapter. You'll want to review that for the exam, however. And then we also talked about being able to oxidize aldehydes. And the other day we talked about using this reagent called the Tollens reagent. This is the demonstration that I'm going to do for you on Friday, so come prepared to watch or watch that particular demonstration. And again, highest exam score will get the silver mirrored flask. So you need to be studying for that next exam. So that's all for today, and you'll have a quiz on PKA. So put everything away. Tina will hand out the quiz, and I'll see you all on Friday.